Hey guys, so today I'm going to talk to you about the topic that I've chosen for our final video project, which is called quantum point contact. So just to give a quick overview of what quantum point contact is, essentially it's a constriction between two electrically conductive regions that's on the order of the electronic wavelength. So it has to be in the sort of nanometer to micrometer scale. Here's a diagram that I found online, and it just sort of shows what I'm talking about. So each side is a conducting plate, essentially, and then the constriction is in the middle, and that's where you're going to have your quantum point contact. So anyways, zooming in a little bit towards that constriction that I was talking about earlier, we can see that at the QPC, electrons are confined in the transverse direction, and only a handful of electronic nodes compliant with the confinement of the electrons and the wave functions of the electrons link the two conductors. So if you have a conductor on the left and a conductor on the right, the wavelength of the electron has to satisfy one of the nodes allowed in the confinement region in order for the electron to pass and for it to be conductive. So with that general sort of overview in mind, we can start to talk about a few of the properties of QPCs. So going back to the transverse confinement, we can say that transverse confinement in the QPC results in the quantization of motion in the transverse direction, not allowing it to vary continuously, but instead be a series of nodes, which are the nodes that I was talking about on the last slide. And like I said earlier, the electrons can only pass through the QPC if it interferes constructively with one of the nodes in the confinement region. So as a result, the conductance is quantized. The conductance across the quantum point confinement, is quantized in terms of the conductance quantum constant. GQ is equal to 2 times charge of an electron squared over h bar. And then the total conductance is given by the expression G is equal to N times GQ, where N is the number of modes, which is determined by the constriction of the quantum point confinement region. These are very interesting properties and yield a lot of potential for applications, especially since the applications haven't really been fully explored, as this is a relatively new sort of phenomenon. So if we look at the history of quantum point confinement, it was actually only first observed in 1988 by a Dutch group and independently by a British group around the same time. One of the results from this group, I believe it was the Dutch group, is they measured the conductance at the point of confinement, which is given by G, and the applied gate voltage. And as you can see, the conduction is quantized, and there's a step in between at each particular point. And also, if you look at the width of the confinement, you'll notice that it's about 250 nanometers, which is small enough to have this sort of confinement effect happen, which is probably why it didn't come about till much later on, because they have to fabricate something with that small of a width. So the historical data that I just showed was for a case where the magnetic field was 0, but magnetic fields do have a very strong effect on quantum point contacts. So in the presence of perpendicular magnetic fields, the modes of a quantum point contact get depleted as the magnetic field increases the local confinement at the quantum point contact. Additionally, there's a correlation that as the strength of the perpendicular magnetic field increases, the width of the conductance plateau increases. And in order to see how this affects the data that was previously gathered with a magnetic field of 0, we can look at this graph on the next slide, which shows the effect that applying a perpendicular magnetic field has on the quantum point contact. So if we look towards the bottom with very wide plateaus, we see a strong magnetic field, perpendicular magnetic field, and as you move up and up, the modes are beginning to increase because there's less confinement, because there's less perpendicular magnetic field, and therefore the conductance plateaus get shorter, and you have more jumps in the conductance at a shorter interval of the gate voltage. Additionally, other aspects do influence the performance and characteristics of quantum point contacts. And one of the big aspects of this is the effect that temperature has on the system. So normally when this experiment is carried out, it's carried out at around like 4.2 Kelvin. In this case, it looks like it's even 1.7 Kelvin. So that's at a very low temperature where you can have very distinctive spacing between the modes. But however, the conductance steps vanish as the temperature increases to a level high enough where thermal energy is approximately equal to the spacing between the sort of modes. So if we look at this diagram below to sort of get an idea of what's happening here, you can see they're set up on the left of the quantum point contact source and drain, and then the confinement region in the middle. And then on the right, you can see the two different experiments performed. One was performed at 1.7 Kelvin and the other at 20 Kelvin. And at 1.7 Kelvin, you have very distinct peaks, sort of like jumps between conductance plateaus. However, even as low as 20 Kelvin, you begin to lose those peaks, and it sort of just becomes more of a quasi upside down parabolic shape. So in order to fabricate the systems that we're talking about in a controlled manner, the best way to do it is you form the QPC in a two-dimensional electron gas. So for example, like gallium arsenide or aluminum gallium arsenide heterostructures, by applying a voltage to gate electrodes, and then that voltage will deplete the electron gas locally in form of plane of quantum point contacts and quantum dots. And another more simple way to create a quantum point contact is actually just to place the tip of a scanning tunneling microscope extremely close to the surface of a conductor and have that sort of act as your point of confinement. So now that we've sort of talked about the properties of quantum point contacts and how you fabricate them and the history of them, it's important to talk about what they can actually be used for. So one of the main uses for quantum point contact systems is as highly sensitive charge detectors. Since the conductance through the contact depends so strongly on the size of the constriction applied at the gate, any charge carriers in the vicinity will influence the current through the quantum point contact. This is because any charge carrier will cause a flux, sort of a flux or fluctuation, if you will, in the potential at the quantum point contact, and this is a potential that can be measured. Also, quantum point contacts can be used in solid-state quantum computing systems as readout devices for the state of a qubit. So here's just a list of the references that I didn't have in the presentation itself. All the pictures have been cited directly right underneath them, and these are just the references that I used for the actual data. And that concludes my presentation on quantum point contacts. Thank you for watching.